The first step to the DC Motor Lab is to build the pre-built model. Selecting the blue Build Model button generates the controller code in the MATLAB window. Next, we open the theta.scope, scope, which will allow us to watch the angular velocity of the motor when it is running. Then, we change the input voltage to one of 3 pre-selected values. For this first run, we chose 5 volts. Now that the environment is set up, we click Connect to Target, and once it is loaded, Start to begin running the motor. The motor responds by ramping up to a velocity determined by the 5-volt input we gave it, and runs without the brake engaged for 10 seconds. This is the view from the scope that is happening simultaneously. Once we have collected the first run's data, it is saved in the MATLAB workspace. We now save the workspace as a file that we can download and analyze later. Now we repeat the same procedure for 2 other voltages to observe how the motor's response differs. The second voltage chosen is 3. The lowered voltage results in a slower angular velocity, which can be seen in the scope view here. After completing this run, we also save the MATLAB workspace to a separate file that we can also view later. The final input voltage selected was 1 volt. This will run much slower than the previous 2 tests. We make sure to save this MATLAB workspace as well for later analysis. The next step in the manual is to change the input from a step to a sinusoidal voltage. We selected the amplitude to be 3 volts and the frequency to be 3 radians per second. The motor's response is now shown to oscillate back and forth with the sinusoidal input. Here, we had to readjust the scope view to include the full range of values and can see the sine wave response. Finally, we save the data as another file for us to use later. The following procedures are from Part C of the DC Motor Lab. Here, we have already opened the Simulink diagram. We enter our gain values into the MATLAB command window with a KP of 10, KD of 0, and KI of 0. Next, we build the Simulink model to generate our controller code. Now we check the theta command block to ensure that the final value is limited to 5 over kp, connect to the target, and run the controller for 10 seconds. Here we see an oscillatory response indicative of underdamping. We save this data from the MATLAB workspace to a file for us to utilize later. Now we change the gain values by introducing KD to observe how it alters the controller's response. Here we see a slow response that doesn't quite reach its desired state, which is indicative of overdamping. We save this data from the MATLAB workspace to another file for us to analyze later. Now we change the gain values by adding Ki and using the gains we calculated during the controller design in Part B. From our designed gain values, we can see a response with quick rise time and minimal overshoot. We again save our data from the MATLAB workspace. Now we run the same test again, but with the brake applied to the motor shaft. Even with the brake applied, our controller still reaches its target state. We save this data from the MATLAB workspace for later comparisons. Now we run the test again, but with a more significant brake applied to the motor. The controller response has a reduced overshoot, but still reaches its target state. We save this data from the workspace again for future analysis. Finally, we remove the break from the motor and reduce the sampling time from happening every 100th of a second to every 10th of a second. Here we can see how the changed sampling time affected the controller's response capability. We save our data from the workspace for the final time and send it to ourselves to conclude the in-person portion of this lab.